This tutorial will illustrate how the CSI Load Optimizer can be used on a bridge model. Here, we will attempt to even out the deck displacements by adjusting the tension in the cables. The cables will be the variables, and the deck displacements the goals. When using the CSI Load Optimizer, there are three classes of problems that can be solved. Optimization, where the number of variable loads exceeds the number of goals. Determinant, where the number of variable loads equals the number of goals. And best fit, where the number of variable loads is less than the number of goals. The model used in this tutorial will be similar to that created for the staged construction watch and learn, except that the moment of inertia of the deck has been reduced so that cable tension will have a larger effect on deck displacements. The sequence of the construction and the resulting moment diagram is as follows. This is the displacement diagram for the bridge at the end stage of the bridge load case. The displacement of the deck at the pylon location is approximately 0.01 meters down. We will use the CSI Load Optimizer to vary the loads in the cables so that the displacement at each of the cable locations is approximately the same, minus 0.01 meters. Successful implementation of the CSI Load Optimizer requires that the user select variable loads and goals that are both relevant and independent. Because this bridge is symmetric about both its width and length, we can take advantage of symmetry to reduce both the number of loads and target goals. The variable loads will be assigned to cables grouped together based on symmetry. For this example, the first set of cables and the first deck segments will be assigned to group Deck 1. The next set of cables and deck segments assigned to Deck 2. And then Deck 3, and so on. The last set of deck segments and abutments will be assigned to group Deck 10, but will not include any cables. Thus, we have a total of 9 groups of cables, so we will have 9 variable loads. A quick review of the bridge scheduler that was used for constructing the model shows how the groups are sequenced. Now for our target displacements or goals. We want the program to adjust the cable tensions such that we have equal displacements in the deck of approximately minus 0.01 meter. Again, because of symmetry, we only need to specify our goals for one side of the bridge, and thus we will have a total of 9 goals. With 9 variable loads and 9 goals, this example will be a determinant problem. We start by going to the Loads tab and defining our variable load pattern, which we will call tension cables. Even though we are adjusting multiple groups of cables, we need only define a single load pattern. Next, we select all of the cables so that we may apply a strain loading. Using the tension cables pattern, we will assign a strain of 0.001. The strain will be scaled when optimizing the cable loads needed to reach the target displacements in the deck. Next, we will create a nonlinear staged construction load case. Which we will call Tighten. Here is where we will tighten the cables. This case will start from our bridge case, which is the construction sequencing case. For this case, we will add load using the tension cables pattern for each of the 9 groups of cables. Starting with deck 1, and ending with group deck 9. Next, we move on to the optimizer, which can be found on the Advanced tab under Tools. The name shown on this form is appended onto the main file name to indicate a load optimizer file. The load case for the optimizer is Tighten. Note how the load assignments table is automatically populated with our 9 variable loads. Next, we can set the number of iterations. We will use 15. We can also set the acceleration factor, and here we will use a value less than 1 because we anticipate that the program will oscillate to a solution. Next, we will define our goals, which for this model will be joint displacements on the right side of the bridge deck. We will start with joint 23, which is just to the right of the pylon. Because the system is symmetric, we need only specify the goals along one side. Our target value for vertical displacement, or U3, is minus 0.01. We repeat this for the 8 other locations along the deck, namely joint 24, through joint 31. With our 9 variable loads and our 9 goals specified, we can now click the Save and Run button. This will start the optimization. Note that LOPT1 has been appended to the file name. This optimization may take significant time due to the iterations required. This message lets us know that the optimization is complete. We will remove the deck from view so that it is easier to see the cable displacements. This is the case at the end of construction. Opening another window, we will plot the same view after the optimization case. Note that LOPT1 has been appended to denote a load optimizer case. Here we can see that the ends of the cables are all at nearly the same elevation. The displacements have been smoothed out. A right click shows that the displacements are indeed approximately minus 0.01 meters, which was our target. If we switch to a display showing the axial loads for both cases, and then right-click on the cable adjacent to the tower, we can see that prior to the load optimization, the cable load was 1,029 kilonewtons. While after the optimizer has been run, the axial force has increased to 1,198 kilonewtons, showing that the tension in the cables was adjusted to achieve the target displacements in the deck. A check of the log file shows that we have 9 variables and 9 goals. And that 13 nonlinear iterations were required to find the solution. This completes this tutorial on the CSI Load Optimizer.